All right. Everybody see fine?
That's good.
Good. Okay. Thought it might be beneficial just at the start here to get a big picture overview of chapter 18. And by the way, the exam does go through chapter 18, though any questions about chapter 18 on the exam would not be any harder than the one that was on the one from 3 years ago. And we will look at that one here, that problem. So the title is Divisibility in Integral Domains. And big picture wise, you're trying to see what you can say about generalizing things like what is a prime, what does unique factorization mean, to arbitrary integral domains. Okay, and again, remember what an integral domain is. It's a commutative ring with unity in which every non-zero element, that's a field, excuse me, with no zero divisors. So that's the kind of thing that we're dealing with here. We are mostly interested in integral domains. And if you've done the reading, which you should have by now, you realize that there are a lot of other domains to think about here as well. But first we need a definition. Definition of what it means for an element to be irreducible and a definition of what it means for an element to be prime. Essentially, the definition of irreducibility generalizes the ordinary definition of what it means to be a prime number. And the definition of what it means to be a prime element in an integral domain generalizes Euclid's lemma. So an element is irreducible if it's not a unit, and if the only factorizations of that element are trivial. If A equals B times C, then either B or C is a unit. And if as you read these things, if you think about your main example, Z, an element in Z, the integers, is going to be irreducible if when you factor it as B times C, either B or C is plus or minus 1, because plus or minus 1 are the only units in Z. On the other hand, again, prime generalizes Euclid's lemma. We define an element to be prime if when it divides B times C, it necessarily divides either B or C. That was something that was proved as Euclid's lemma back in chapter 0. Here in chapter 18, we take it as a definition. And we're wondering, one thing we're wondering at least is, are these definitions equivalent to each other? And the answer is, sometimes they are, sometimes they're not. And that's why it's worth having two separate definitions. One real important kind of example to consider here are these rings, well, in general, Z square root of D, which as a set consists of all complex numbers, possibly complex if D is negative. These would be real numbers if D is positive. A plus B times square root of D, where D is not 1 and is also not divisible by the square of a prime. You might wonder, is it okay to be divisible by other squares? Well, we won't get into that. Let's ignore this part for the moment here. The point of example 1 is that when D is -3, you can prove that there is an element of this ring that is irreducible but not prime. So they're not equivalent. This is one example of a ring where there are irreducible elements that are not prime. We'll come back to the proof of this when we look at the example from the test, but just realize that is the main thing to conclude, is irreducibility and prime are not equivalent. On the other hand, this theorem says that in an integral domain, every prime is irreducible. So prime implies irreducible in an ID integral domain, which is the setting that we're talking about anyway. We're always talking about integral domains here. prime implies irreducible. Okay, but by that example, irreducible in general does not imply prime. If the only factorizations are trivial, the analog of Euclid's lemma is not necessarily true. However, there is a special case, a special situation where irreducibility and being prime are equivalent in a principal ideal domain. In a principal ideal domain, an element is irreducible if and only if it is prime. We could add, in a principal ideal domain, which is an integral domain, irreducible does imply prime. What was a principal ideal domain? That's something you should certainly be able to define on the exam. Anybody want to remember off the top of your head?
All of the ideals are principal ideals.
Yep. All the ideals are principal ideals. The analog of cyclic groups. They're of the form that they're generated by a single element. A, and by definition, this set is the set of all multiples of A as R varies over the ring. Every ideal is of that form. That's a principal ideal domain. So when that's true, then irreducibility implies prime. When you got only trivial factorizations, it implies the analog of Euclid's lemma. You might wonder, it seems like we've been dealing with things that are just principal ideal domains. And in fact, back in chapter 17, I think, or no, I think it was 16. In chapter 16, we had a theorem that said if F is a field, that's, again, the situation where it's a commutative ring with unity in which every non-zero element is a unit. Then Fx, the polynomial ring with coefficients in F, is a principal ideal domain. Remember, I've emphasized this a lot, so maybe this is going to be a true-false question or something. This thing right here, this polynomial ring, is never a field, even when F itself is a field. Never, ever a field. But if F is a field, it is a principal ideal domain. Have we had any examples of things that are not principal ideal domains? Yeah, but I don't think we've explicitly said it before chapter 18. According to example 3, Zx is not a principal ideal domain. And the claim to prove that is that this ideal, generated by 2 and x, is not a principal ideal. It's not of the form generated by h of x. Which makes me remember that we haven't really emphasized what this notation here means. Let me just write down the conclusion here. Zx is not a PID. This ideal generated by 2 and x turns out to not be a principal ideal. But what is this by definition? This is the set of all You might call them linear combinations of 2 and x. Maybe call them R1x times 2 plus R2x times x, as R1x and R2x vary over the ring. That's what this notation is defined to be. Linear combinations of 2 and x, where the coefficients are polynomials in zx. That is an ideal. You can prove it's an ideal. And again, according to example 3, it can't be written as a principal ideal. It cannot be written as the set of all products of h of x times some arbitrary ring element. Okay, and you have to go through this proof to understand that. But we're again just trying to get an overview here. Of course, there's a lot more still here in chapter 18. The idea of a unique factorization domain, UFD, and then we'll also see the idea of a Euclidean domain, an ED. An integral domain is a unique factorization domain if essentially, by definition, the fundamental theorem of arithmetic holds. If you imagine D being Z, Z is a unique factorization domain. Every non-zero element that is not a unit, not plus or minus 1 in Z, can be written as a product of irreducibles in D. And if D equals Z, which Z itself is a principal ideal domain. So while ZX is not a principal ideal domain, Z is a principal ideal domain. So irreducibility and being prime are equivalent in Z. To say that every non-zero element is a product of irreducibles means it's a product of primes in Z, because irreducibility and being prime is equivalent in Z. And the factorization is unique up to associates and up to the order in which the factors appear. You can rearrange the factors for one thing, so the order that they appear is not unique. And when it says up to associates, effectively that means up to plus or minus the irreducibles. So for example, the primes you could be thinking of as being, for example, 7 is a prime and -7 is a prime, but 7 and -7 are what are called associates. 7 is -1 times -7, where -1 is a unit. That's in the definition of associates, which I didn't talk about here. So UFDs are where unique factorization holds. Let's skip this part for the moment. Let's look at this one. PID implies UFD. Every principal ideal is a unique, every principal ideal domain is a unique factorization domain. So if all the ideals are principal ideals, you can prove that factorization in terms of irreducibles is unique, exists and is unique. The proof of that requires this lemma, which I don't want to go through the proof. We're just trying to get the big picture here. As a corollary, if F is a field, then this is a unique factorization domain. Why? Well, we already know if F is a field, then F of X is a principal ideal domain. Therefore, it's a unique factorization domain. So you got the analog of the, again, the fundamental theorem of arithmetic holds in this situation. It actually holds more generally when we're talking about ordinary polynomials. Let's see, I forgot, it is in chapter 17. You actually do have unique factorization in ZX even though ZX is not a principal ideal domain. So you can have the theorem that we just looked at says if you're in a principal ideal domain, you're guaranteed unique factorization. But Z of X is not a principal ideal domain, so we would not be guaranteed unique factorization based on those theorems in chapter 18. However, it does turn out to be unique factorization domain anyway. Okay, is what this says. The final part of chapter 18 is about one more kind of domain called the Euclidean domain. And a Euclidean domain is essentially a situation, you've got an integral domain where you've got this function d called a measure that essentially generalizes absolute value, and it also generalizes the degree. And in fact, those are the two main examples they talk about here initially. Z is a Euclidean domain. We can take this measure d to be defined to be the absolute value function. And f of x is a Euclidean domain when f is a field. You can take the d function to be the degree of f, and it satisfies these properties. Notice the second of which is a property related to the Euclidean algorithm, division and remainders. We can, when we're dividing a by b, there's a quotient q and a remainder r, where either r is 0 or d of r is less than d of b. The absolute value of r is less than the absolute value of b, or in the polynomial case, the degree of r is less than the degree of b. Couple more facts here. Every Euclidean domain is a principal ideal domain, and therefore also a unique factorization domain, because we know principal ideal domains are unique factorization domains. So you have this sequence of implications here. Every Euclidean domain is a principal ideal domain. Every principal ideal domain is a unique factorization domain. And it's very fortunate, as the author remarks, that these go in alphabetical order: ED, PID, UFD. You might remember on Moodle, we've got this picture here as well. I probably should have put this in this week instead of last week. Every Euclidean domain is a principal ideal domain. Every principal ideal domain is a unique factorization domain. And therefore, every Euclidean domain is also unique factorization domains. And these are all integral domains. Fields are the most specialized. They are all of these as well. So that's kind of a nice thing. But again, it goes in alphabetical order here with ED, PID, and UFD. That's the way to remember it. And we can close off chapter 18 by emphasizing this example. This is an integral domain, but not a unique factorization domain. In other words, this example, z square root of -5, is inside the red circle, but not inside any of these other circles. It's an integral domain that's not a UFD, and therefore it's not a PID, and therefore it's also not an ED. It's definitely not a field. Why? Let's try to take a look at the proof of this, and then we'll relate it to the exam question. So, well, first of all, they say it's straightforward to verify it's an integral domain. It would not have any zero divisors. Its unity would be the number 1 when a is 1 and b is 0. To verify unique factorization does not hold, you got to come up with an example that's got two distinct factorizations in terms of irreducibles, where the irreducibles are not associates of each other. So the claim is that this would be two factorizations of 46 in particular, 2 times 23 and this times this. And evidently these things, 2 in this and 23 in this, none of these are associates with each other. Hang on here a second. How'd they come up with this example? I don't know, some experimentation, okay? Of course, the author does things like this where he kind of pulls things out of a hat. But once it's pulled out of the hat, we can try to understand it at least. We claim they're all irreducible. He doesn't prove all of them are irreducible. Looks like he starts by proving 2 is irreducible, which makes intuitive sense because 2 is prime in the integers. You would think it would be irreducible even in this ring, but it does take proof. So what does it mean to be irreducible? It means it only has trivial factorizations. If you factor it as x times y, then either x or y is a unit. Yeah. So looks like this is an argument by contradiction, actually. Suppose we got a non-trivial factorization. So suppose x and y are both not units. Neither is a unit. Evidently, we're going to get some kind of contradiction. So this is where the author applies a common argument that I haven't talked about yet here in applying the norm function and using its properties. And on the exam question, that's part of the exam question as well. In general, the norm in this ring, z of square root of d, is a function that takes this element of that ring and maps it to this non-negative number, the absolute value of a squared minus d times b squared. For our example that we're just looking at here, d is -5. So this would really simplify to the absolute value of a squared plus 5b squared, since d is -5. And since we're adding a squared plus 5b squared, and a squared and b squared are not negative, we actually don't need the absolute value signs when d is negative. There's the expression a squared plus 5b squared. No need for absolute value signs. This norm function has properties that are key to using it to prove things. One property is that it equals 0 if and only if the element is the number 0, if and only if a and b are both 0. N of xy is n of x times n of y. X is a unit in the ring, has a multiplicative inverse if and only if n of x is 1. And if n of x is prime, then x is irreducible. By prime here, we mean prime number. N has outputs that are positive integers. So we're talking about a prime number there. If n of x is a prime number in the usual sense, then x is irreducible in this ring. So how are those properties used here? Well, n of 2 does equal 4. In the formula here, if you replace a with 2 and b with 0, you get 2 squared plus 5 times 0 squared, you get 4. So n of 2 equaling 4 is just the formula for this norm in this ring. Saying that equals n of x times n of y is based on the fact, based on this property. And the fact that we're assuming 2 equals x times y. N of x and n of y are both integers. And neither of them can equal 1. The author doesn't say that here. Doesn't mention neither one can equal 1. The author, sometimes leaves some details for you to realize. Since we're assuming neither is a unit, that means n of x and n of y are not equal to 1 because of the fact that x is a unit if and only if n of x is 1. So neither one of them is 1, and therefore neither one is 4 either. They must both be 2. But that's impossible. There's no way you can pick integers for a and b to make one of these expressions equal 2. I mean, we're not explicitly proving that here, but it's pretty obvious. Certainly if A and B are both 0, this is not equal to 2. If A is 1 and B is 0, it's not equal to 2. If A is 2 and B is 0, it's not equal to 2. If A is 1 and B is 1, it's definitely not equal to 2. If A is 0 and B is 1, it's definitely not equal to 2. And bigger values of A and B, including negative values, are not going to produce anything different. There's no way such an expression can equal 2. That's your contradiction, which is impossible. You can do a similar proof with the 23. They say the same argument applies to these other numbers. Maybe we should try to see if we can figure out how that argument goes. Any questions? Please pipe in if you do. So we're wondering, we're claiming, for example, that 1 plus 3 square root of negative 5 should be irreducible. Again, use an argument by contradiction. Try to mimic what the book does. Say it's a product of two elements, and say for the sake of contradiction that neither of those elements is a unit. Suppose, to the contrary, that neither x nor y is a unit. We claim that one of them must be, because we claim that this thing is irreducible. So you do an argument by contradiction. So we got to apply this norm function and use its properties. If I take the norm of both sides, I can say this is true. But what does this equal? It equals 1 squared plus 5 times 3 squared. 3 squared is 9, plus 5 is 45, plus 1 is 46. Okay, the argument here would be definitely trickier here, I think, but if we were going to do it fully. Since neither x nor y is a unit, neither of these numbers is 1. And also neither of them is 46. Therefore, you could say without loss of generality, one of them is 23 and one's 2. Say n of x is 23 and n of y is 2. I'm doing a without loss of generality here because I could also can say n of x could be 2 and n of y could be 23. But that's in a symmetric kind of thing. So you may as well just assume n of x is 23 and n of y is 2. Evidently, both of these things lead to contradictions. Definitely saying a squared plus 5b squared equals 2 is a contradiction. And that, I guess, would be good enough. You only need one contradiction. Evidently, it must be true that there are nothing you can choose for integers a and b to make that equal to 23. That's less clearly a contradiction. It's less clear that there's no way you can make 23. The argument's going to be harder, excuse me, if the number is bigger. I mean, there's only a finite number of things to try for a and b, and I'm not going to take the time to try them all. Probably best just to focus on that giving you a contradiction. Clearly, there's nothing you can choose for a and b where this is going to equal 2. And that would be enough to say we've got a contradiction. So this assumption must be wrong, and therefore either x or y is a unit, and therefore 1 plus 3 square root of negative 5 is irreducible. With the exam question from 3 years ago, it's the same kind of example here. Same integral domain, actually. Same norm, which has the same properties. Claim it's not a unique factorization domain, which is what the book's example claims as well and proves. Instead of factoring 46 in a couple different ways, I factor 21 in a couple different ways. Which does bring up another question, though, is could these be associates? And the book actually didn't address that. I think the author must be just assuming you say they're clearly not associates. The only, okay, that's actually, it is pretty clear. The only units are plus or minus 1. In fact, the only way you can get 1 out of that expression is if A is plus or minus 1 and B is 0. And we know X is a unit if and only if n of X equals 1. So yeah, there's no way these can be associates because being associates means they're plus or minus 1 times each other, a unit times each other. So it's definitely something to note, but the author is essentially assuming you're going to look it up. You're going to realize that yourself. So essentially, it looks like the task on this problem is to do the exact same thing we just did. Finish the proof by proving that this is irreducible. So it's an argument by contradiction again. Assume to the contrary, it equals x times y, where neither x nor y is a unit, and apply the n function and do the same kind of thing we just did. If you plug this into the n function in this case, you're going to get 1 squared plus 5 times 2 squared. That'll be 21. And the contradiction is going to be that something like that could either equal 3 or 7. And that's impossible. There's no way, for example, that this expression can equal 3. You know, again, you can try small values of a and b, 0, plus or minus 1, plus or minus 2. It becomes pretty clear very rapidly that there's no values of a and b that are going to make that equal to 3 or 7 for that matter. Okay, so it's pretty much what we just did. Any questions? Let's glance over the rest of the exam here from 3 years ago. Definition of a ring here. You can either write down the properties symbolically or you can describe them with words. You want to get it right, so don't add any unnecessary properties. In particular, in the definition of a ring, there's no assumption that there's a unity. Anytime we've got a ring with unity, we say, suppose R is a ring with unity. So you should not assume there's unity in your ring in the definition, in the abstract definition of a ring. You should also not assume that multiplication is commutative. Anytime multiplication is assumed to be commutative, we say, let R be a commutative ring.
If you put this, sorry, really quick, if you put this on the test, I remember in class you just said that R is an abelian group under addition. Is that good enough, or because the book like separates it and gives all of those?
Yeah, you could do it either way.
Okay, great.
Yep. You could say it's an abelian group under addition. That would be good enough. And then say what the multiplication property is. It's satisfied. It's got closure for one thing, and then so it's a binary operation. It satisfies associativity. Multiplication satisfies associativity, and then there's 2 distributive properties: left distributive property and right distributive property, and you need to state them both in the general case of the ring because you're not assuming it's commutative. Define what it means to be a unit, zero divisor. Oh, here we go. One sentence definition of what it means for F to be a field. You may assume in this one sentence that you know what a commutative ring with unity is. And you also need to assume you know what a unit is. I'll let you think about that. I've said that a number of times. Here I'm letting them state either the definition of an ideal or state the ideal test. Principal ideal generated by A. What is it? And then define what it means to be a principal ideal domain. Here's a chapter 18 one. What does it mean to be irreducible? I could also ask, what does it mean to be prime? And they are different. Remember this one? Is Z an integral domain for any positive integer n? It's certainly a field if and only if n is prime. Do you remember? Think maybe Z4. Does Z4 have any zero divisors? What's 2 times 2 mod 4?
Just gonna say 2 is a zero divisor, isn't it?
Yeah, 2 times 2 is 0 mod 4, so but 2 is not 0. So 2 is a zero divisor, and therefore Z4 is not an integral domain, and that would be enough to say this is false. In fact, if n is not prime, Zn will not be an integral domain. There will be zero divisors. What about this one? The only ideals in a field are trivial or the entire field itself. I did talk about that, though. I didn't really talk about it directly, but there was an example, and I said it was an important example that we talked about related to ideals in fields. That is enough to tell you whether this is true or false. The fact that we talked about that's related to this is that if the unity 1 is in an ideal of a field, then in fact that ideal is the entire field. If 1 is in the ideal. I also said if the ideal in a field contains a unit, it must be the entire field. What do you think? True or false here?
True.
It's true, yeah. Because, yeah, if you were after some non-trivial ideal, since it's a field, all non-zero elements are units, that ideal would have to contain a unit. It would therefore, it turns out, also have to contain 1, and therefore it would have to be the entire field. The only ideals in a field are the trivial one and the entire field itself. So the theory of ideals is not very interesting in the case of fields. You would never form a factor ring where the starting ring is a field, because it's just not interesting. Okay. Ideals are only interesting in the case of rings that are not fields. Well, these other ones are related to stuff we just talked about today. And let's look at 14 in detail here. Consider a ring homomorphism from Z12 to Z20, where phi of 1 equals A is in Z20. Use facts that must be true about the order of A and the fact that A squared equals A in Z20 to determine the possibilities of A. And the order of A here is referring to its order as a group element under addition. So this is supposed to be a ring homomorphism. Since these rings, as all rings, are also groups under addition, it's also got to be a group homomorphism. Under addition. So, given an element A, well, okay, so we're assuming phi of 1 equals A for some number A. It's got to be equal to some number A because 1 has to get mapped to something. That number A being in Z20 implies that the additive order of A has to divide 20. By Lagrange's theorem. Also, the additive order of A has to divide 12. Let's see, do we have a theorem that explicitly talked about that here? I'm looking back in chapter 10 here. On group homomorphisms. There's a similar example here. Example 10 in chapter 10. They're trying to determine all group homomorphisms from Z12 to Z30. Lagrange's theorem and property 3 of theorem 10.1 require A divide both 12 and 30. Property 3 of theorem 10.1 says if the order of the input is finite, then the order of the output must divide the order of the input. The input here is 1. Its order is 12 in Z12. The order of the output has got to divide 12 as well then. Also, the order of 1 is 12 in Z12. So the order of its image, which we're calling A, must also divide 12. Theorem 10.1.3. So the order of A, whatever it is, has to divide both 20 and 12. So that limits what the order of A can be. It could be 1, it could be 2, it could be 4. Is that it? That looks like that's all the possibilities. Talking the additive order as an element of Z20. So that means A itself, What has order 1 in Z20? 0. What has order 2 in Z20? 10. What has order 4 in Z20? There's 2 elements, 5 and 15. That has order 1. That has order 2. And both of these have order 4. So that has limited the possibilities a lot. We're also told to use the fact that a squared equals a in Z20. In other words, a must be idempotent. Why? Why must it be idempotent? Nothing we've done so far explains why it must be an idempotent. Well, it's related to the fact that being a ring homomorphism, phi is not just operation preserving under addition, but also operation preserving under multiplication. We know phi of 1 equals a, but this also equals phi of 1 times 1. Since 1 equals 1 times 1, and phi is operation preserving with respect to multiplication, this also equals phi of 1 times phi of 1. In other words, a times a. So no matter what, a squared must equal a. Now technically 0 satisfies that. 0 squared does equal 0. Technically, we don't say that's an idempotent because with idempotents, we focus on non-zero elements. But it's possible with these non-zero elements, the 10, the 5, and the 15, it's possible for some of them to be idempotents and some of them to not be. You have to check it and see what happens. 10 squared in Z20, mod 20 is 0. So 10 is not idempotent. A cannot equal 10. How about 5 squared? 5 squared is 25, mod 20 is 5. 5 is a possibility. It is an idempotent. How about 15? 15 squared is 225. Mod 20 is 5. Right? Just double check that I didn't make a mistake there. 15 squared, yep, 225. Mod 20 is 5. So 15 is not idempotent. So there's only two possible answers. A is either 0 or 5. 0 squared, of course, does equal 0.
Why is 15 not?
Because it doesn't equal 15. 15
Oh,
squared
then
doesn't equal
15. That's just
5.
right. Thanks.
A equals 0 or A equals 5. There are only two ring homomorphisms from Z12 to Z20. By the way, if A is 0, then it's a trivial ring homomorphism. It's mapping everything to 0. If we're in the case where A is 5, I could also ask you, figure out the output at some other value of the input. So if phi of 1 equals 5, what does phi of 2 equal? And it's probably best to use the fact that phi is operation preserving under addition to do that. 2 is 1 plus 1. So this is phi of 1 plus phi of 1. 5 plus 5 is 10. More interesting example would be maybe something like, how about phi of 11? 11 would be 1 added to itself 11 times. That's going to be phi of 1 added to itself 11 times. In other words, 5 added to itself 11 times. Which would be 55, and then mod by 20, that's going to be 15. Okay, so you should be able to do that kind of calculation as well. This one's the long division problem with mod 3 arithmetic, it looks like. Figure out the quotient and remainder. This one's from chapter 11 about finite abelian groups. How many abelian groups are there of this order? Show your work or briefly explain. And the key, if you recall, to doing this quickly at least, is to figure out how many partitions there are of the exponent 5 and how many partitions there are of the exponent 3 and multiply those answers. So the exponent 5, how many ways are there of partitioning 5? There's 5 itself, there's 4 plus 1. There's 3 plus 2, there's 3 plus 1 plus 1. There's 2 plus 3, but you don't have to rewrite that because it's already been done as 3 plus 2. We don't consider 2 plus 3 to be distinct from 3 plus 2. But there is 2 plus 1 and 2 plus 1 plus 1 plus 1. And 1 plus 1 plus 1 plus 1 plus 1. Always feels a little worrisome about whether I've found all of them here. I've been systematic about it here. Yeah, it's going to be all of them. Again, I don't have to write 2 plus 3 because that's already taken care of with 3 plus 2. 2 plus 1 plus 2 is equivalent to 2 plus 2 plus 1. How many partitions? 1, 2, 3, 4, 5, 6, 7 of them. 7 partitions of 5. With the other exponent 3, there are 3 partitions of 3. So altogether, you've got 7 times 3 equals 21 abelian groups of order 2 to the 5th times 3 cubed. And each pairing of, say, one of these partitions with one of these, you should be able to also write down an abelian group that corresponds to those. In other words, 2 to the 5th here is that's 32 there, and this is 3 cubed is 27. For the partition 3 plus 1 plus 1, a group of order 32 that corresponds to that partition would be z sub 2 cubed, which is 8. External direct product with z sub 2 to the 1st. External direct product with z sub 2 to the 1st. The exponents, 2 cubed, 2 to the 1st, 2 to the 1st, 3, 1, and 1 correspond to the 3 plus 1 plus 1 partition of 5 here. And then for this partition of 3, the 2 plus 1, groups of order 27, an abelian group of order 3 squared would be Z9. And one of order 3 to the first would be Z3. So the powers of 3 in this case, 3 squared and 3 to the first, powers are 2 and 1, corresponds to this partition of 3. So this would be the example of an abelian group of order 864. That's one of those 21 groups. It's the one that corresponds to these particular partitions of 5 and 3. Of course, you can rewrite the order of these and you get an isomorphic group, so you don't have to write it in any particular order. I mean to say other orders are possible. Other orderings of these groups in this external direct product. Here's our fundamental fact that we were just talking about a little while ago. In fact, it's true even when the ring is not a field. Notice I'm not assuming R is a field here. If 1 is in the ideal, then the ideal has to be the entire ring. That's true for any ring. But for a field, 1 would automatically have to be in a non-trivial ideal. And therefore, well, initially, a non-trivial ideal would have to contain a unit. And ultimately, that would mean that 1 would have to be in the ideal as well. And this fact would imply then that the ideal is the entire field. Prove something's irreducible over Q. Tell you what to do there. That's what we focused on Monday. And we did focus on this kind of problem on Monday as well. I think that's about all I have here. Do you have any other questions at all? Of course, this was not a thorough review of other things since chapter 11. Other things include, what's a prime ideal, what's a maximal ideal, theorems related to that. Other irreducibility tests, including Eisenstein's criterion. I didn't put it on the exam from 3 years ago, but I'm not ruling it out. You should know Eisenstein's criterion. In the lecture, I did talk. Go ahead.
Oh, I just can you remind, where does this exam start again, as far as chapter? The chapter 11?
Essentially, chapter 11. In the last exam, we went through chapter 10, though it wouldn't be bad to study chapter 10 as well. Chapter 11 was the fundamental theorem of finite abelian groups related to this kind of stuff. And then we got into ring theory. Wouldn't be bad to have chapter 10 in mind as well, group homomorphisms, especially for problems like we're doing here. And then, then it's ring theory. And I guess the main thing I have not focused on today or Monday really so much has been maximal and prime ideals. In one of the lectures, I did talk about something called the rational root theorem. And I did that just for your information. I probably won't test you on that. So main tests for irreducibility from chapter 17 to be able to use would be the mod P irreducibility test, Eisenstein's criterion, and also the reducibility test for degree 2 or 3, which remember does hold in one direction, even if the degree is higher than 2 or 3. the right to left direction holds even when the degree is higher than 2 or 3. If f of x has a 0, then it's going to be reducible.
When you say that holds, does f still have to be a field?
Yeah, it's still got to be a field, still in the same setting.
So since z is not a field, would this not work in z?
Right. And here's an example that illustrates it. This polynomial is reducible over z, even though it doesn't have any zeros in z. You can factor it like this, and neither 2 nor that is a unit in zx. The roots of this are going to be plus or minus square root of 2i, not real numbers. But because we can factor it in, neither 2 nor that is a unit in zx, technically speaking, it is reducible over z. Not q, though, because these are 2 is a unit in qx. Its inverse would be 1/2. But it's not a unit in zx. All right. It would be good to watch lectures 31A and 31B too, and you'll get more review as well. Have a good day.
Another question, Dr. Kinney.
Yeah,
So
okay.
how is the exam gonna work on Friday?
We'll take it
We're
over
just
Zoom.
gonna just do it over Zoom, and we'll just
Yep.
print it out and then
Yeah. I'll
Scan it
email
into
to you
you?
about. Tell you what, I'll email it to you about 7:25, and then you can print it out. You don't have to print it out if you want to. Just look at it on your screen. You can just tell me I'm looking at the exam on my screen. If you don't have a printer.
Well.
But just wait to start until 7. Excuse me, I guess we have more time, don't we, for exams? So we start the exam at 7:20. So I'll email it to you about 7:05. Okay?
Okay. Thanks.
All right. We'll see you.